Now the recording should start. And again, start sharing. I said about the objectives, enable modeling and subject matter experts to create modular ontologies and reference data based on an IDO. And it does also the goal is to develop interoperability between major standardized data models and reference data libraries. And I listed a few here: DEXP, CFOS, PCA reference data, and also ISO 15926 and ISO 10303. And there are really quite a long list of standards, between 25 and 30 standards have been listed in the IDO project. Have been listed in the PVN project, excuse me. We will also touch the role of IDO within the information modeling framework, IMF, that will come later in this series of sessions. And we really hope that we will be able to create an OBI community that can have a forum for that. The training has been developed for 3 projects, as mentioned here. The DISC project, which is a project between 4 Norwegian companies: Equinor, Aker BP, Aker Solutions, and ABER. And the Arrowhead fPVN project, which is an EU project with approximately 40 participants around Europe. And also Integrated Lifecycle Asset Planning, the project there, which is a project between Equinor, Aker BP, Vår Energy, and ConocoPhillips. We will have 3 types of sessions: presentation and discussion of major standardized data models. That's one of the sessions that we had last Friday on DEXP, and this is also one of those sessions, this time on IDO. And we will have questions and answers and forum sessions. Next session will be for that. And we will have a practical modeling session in smaller groups where we will try to solve particular problems which will arise. And so far we have planned this thing for the rest of this year, but we anticipate that it will go on next year also. So today, meeting number 2, as I've said, I mentioned a little bit about what the plan for the training is, and the main thing is about the presentation of IDO, and hopefully we will have a little bit of time after that for a discussion and just review the plans for the rest of the workshops. And in this, I send it out together with the agenda. You have this plan for the first sessions, which is coming up after this also. So with that, I think I will stop sharing and ask Dirk to take over. If there are any questions before Dirk start the presentation of IDO, we can take it now if it's a quick question. Otherwise, we will wait until the end of this meeting. Okay, I think you can go ahead, Dirk.
Yep, thank you, Nils. So I'm doing this in presentation mode. Now I don't see you anymore. So please let me know if there's an urgent question, so we can maybe react to it. Okay, so welcome to this session on IDO and its role in enabling semantic interoperability. There are lots of people attending these sessions, which is very nice to see. So thank you for that. I think last time we had around 60 people, and this time it seems to be similar. Of course, people have different backgrounds, and not everyone is going to work hands-on with IDO. So it's a bit difficult to cater for everyone's interest. But as Nils was mentioning, our focus is really to enable people to start working with IDO. Nevertheless, I try to provide a bit more background on IDO and I hope we can reach everyone in this session. As Nils mentioned as well, there's very little time, and if you have questions, please just put them in the chat. If we get to it at the end of this 1 hour, then we can answer them there. Otherwise, we will read them all and we will answer them offline or in the next session. Okay, so I'm going to talk about a very simple structure. Just 4 points. I want to say first something about the standardization effort of IDO, about interoperability with IDO, and there we need to have a quick detour into what ontologies are. I will keep this very short, and then we dive into the industrial data ontology and how to get started with it. Okay, so let's start with standardization. So semantics has been recognized as addressing the key business challenges, that is data integration, interoperability, knowledge management, optimization in supply chain, asset management, risk management, and so on. And IDO, the industrial data ontology, is just all about semantics. So what is IDO? IDO is a ontology formulated in the web ontology language as standardized by the W3C. It allows for precise modeling and enables automated reasoning. Now, as so many things, we stand on the shoulders of giants. IDO has been derived from or inspired by mainly 2 other standards. One is the ISO 15926 Part 2 data model, which you could argue is also an ontology, and the basic formal ontology, which is standardized in ISO IEC 21838 Part 2. And this standard is about top level ontologies. We shy a bit away from calling IDO a top-level ontology. We call it upper-level ontology. It is mainly developed in the Norwegian oil and gas energy sector, and it is applied in several others. Here on the right, you see a screenshot of the class hierarchy provided by IDO. We will get to that later. Okay, so the main goal is to provide a common digital language that allows us to integrate reference data libraries that are standardized in different standards in the SC4 and also outside of it. And IDO sits on top of that pyramid of vocabulary. IDO provides the most generic and abstract notions that everything else aligns to. So when you look at this pyramid picture, on top you find IDO, and then in a layered fashion, when we go down, we come to a core level, domain standards, industry standards, and industry applications, and we go to more and more domain-specific terminology. And all of that aligns with the main categories as provided by IDO. This is the idea. A bit about the history. It all started around 2008 with a joint industry project in Norway. So many Norwegian companies involved there. And this effort then continued, and the ontology, back then not called IDO, was refined and documented in the EU project Optique. And then first implementations followed in 2015 already, together with Able and Aker Solutions. Then the need for standardization became clear, and this was presented to ISO, and a draft technical report was proposed and developed. And later a working draft for full international standard was proposed. However, we hit a little roadblock there. There was some disagreement. And after the conclusion of a special ISO study group, the IDO, so the technical report and the working draft were withdrawn from ISO, and a new standard series even was proposed. And this is where we are at the moment. And the new standard is ISO 23726. This is a multi-part standard, and IDO will be part 3 of that standard. All this effort is supported by several companies in different industry sectors and academia as well. Their requirements provide motivation for us to work on it. They need a stable reference to secure investments. They want to make sure the quality is assured and necessary improvements are made to the ontology. And this happens through the ISO standardization process and the community involved in developing IDO. What is needed is a common language to integrate several standards and information models across industries. What is needed as well is a support for automated verification, validation, and quality assurance. And of course, the ontology should be kept as simple as possible and as usable as possible. Now, this is IDO. IDO is the initial part of this new ontology-based interoperability standard, multi-part standard. But of course, it is not part 1, it is part 3. Part 1 is going to be on an overview and providing fundamental principles. Part 2 will provide terms and definitions. Part 3 is an IDO. And part 4 will be on conformance to the standard. And then there are other parts planned on scheduling, the use cases that are in development already will be put in a part, and also the information modeling framework developed in the DISC initiative will find its place in that multi-part standard. So I talked about use cases. There are 7 of them that are currently being worked on. I will not really go into detail here with these use cases. However, I will include a list of slides at the end of this presentation where you can find more information about these use cases and contact information in particular in case you want to get involved. So what is the outcome of this standardization process? Well, it will be a document, a draft international standard here on the left. It looks like that. It will be an electronic insert, which is the ontology that will be made available for free. And of course, the use cases will be documented on the PCA website. Looking forward, we are almost there, actually. A lot of work has been done. Currently, we are working on resolving ballot comments. And the next meeting, the next ISO meeting will be in October, so very soon in Stavanger. In November already, the draft international standard is due. So we have to submit it. And then if everything goes well, fingers crossed, next year, September, we have a new draft. We have a new international standard. If things don't go so well, this project terminates at latest October 26. Now, where are we now? we have a new version 3.0, published at PCA. So you can go to the RDS POSC Caesar org website, look at the version 3.0 of IDO, and you can copy that identifier of the ontology and load it in Protégé, and then browse through the ontology. All the necessary information is included in the ontology. Okay, of course, you can engage. There's a new working group under SC4, working group 26. You can engage in there via your national standardization body. You can also join the IDO consortium developing IDO. You can do that in kind or with financial commitments. Please contact the project manager, my colleague Paul Rülandsholm at DNV. Your organization can also join the POSC Caesar Association. Okay, I think that is all I want to say about standardization. And I would like to now talk about, at least briefly, about interoperability. Interoperability is, of course, everyone's concern. In particular, it's a focus of the Arrowhead fPVN project that focuses on interoperability between standardized data models. Now let's just recap what this is all about. Interoperability is about exchanging data correctly and consistently. There are two integration scenarios to consider. We have point-to-point integration and sort of this star-shaped hub-and-spoke type of integration. The point-to-point integration offers a direct communication between the systems. The challenge there is maintenance, scalability, and the lack of flexibility if you need to modify something. The mappings are on a data level. That is, you can think of it as a field in a structured data of system A is mapped to another field in another structured data format in system B. So it's very concrete, low level. In the star-shaped integration model, there we have indirect communication. So the systems don't talk to each other directly, but via a central hub. That has a little overhead to begin with. However, it is easier to scale, to maintain, and to modify. Here we talk about alignments to achieve semantic interoperability. And that is mainly about harmonization of concepts. So suppose two systems talk about a sensor and a probe, and then you can harmonize that by introducing a measurement device, for example, as a term. Now, looking at the number of connections between these different integration scenarios, you find on the top in the point-to-point integration, there are quadratically many connections in the number of nodes, and in the lower, in the star-shaped integration model, there are only linearly many connections in the depending on the number of nodes. And clearly, the star-shaped version is preferable when it comes to scalability and maintainability. Now, looking at these connections, we find an easy case. The easy case is when the source model is actually more detailed than the target model. Then we just leave out details and we are done. We can communicate with the target. The other way around is hard. If the source is actually less detailed than the target, then it seems we have to add information. How do we do that? We need to uncover hidden assumptions. Maybe there's something hard-coded in the system. We need to make a background knowledge explicit, or consult other data sources to fill in all the details as required by the target system. Another hard case, potentially hard case, is when source and target systems have different expressivity. So they say things in a way that cannot be stated in the other system. Either way is potentially hard. Now we in DNV, this slide is not showing well. We looked at reference designation systems. There's in DNV, we have the vessel information structure. which is a model to describe ships. And SFI is also a coding system for describing ships. And you see here that nodes in SFI map actually to several nodes in the vessel information structure model. And that means this is simply more detailed than the SFI nodes. So one direction is easy, going from this to SFI, because we simply leave out details, but the other direction is hard. So the challenges are the different levels of granularity. So transferring from high to low granularity is easy, but not the other way around. Different node may be similar, but not exactly the same. So the question is how to resolve that. A user often adds their own custom nodes to the SFI model. So how to manage these changes. And we may have differences in terminology. Okay, so ontology-based interoperability is this related to the star-shaped integration picture, where in the middle, in the hub, we envision there to be an ontology-based or an ontology, modular ontology architecture actually based on IDO. The table here on the right compares a little bit the scenario between direct mapping and mapping via an ontology. The initial setup cost is lower when we map directly, lower than when we map via an ontology, because we need to create the ontology to begin with. However, the mapping complexity is higher with direct mappings. The scalability is poorer and the flexibility is limited. The direct mappings are also more prone to errors and inconsistencies, and the long-term effort is actually high. So depending on the size of and number of communicating systems, of course. So using ontologies promises some benefits, and that is a shared understanding via a well-defined and a vocabulary of uniquely identified terms with consolidated term definitions. We have modularity and extensibility, consistency, semantic interoperability, scalability, and quality assurance via automated reasoning. This is all I want to brush over on interoperability. I feel now that we have touched upon ontology, we do need to say a little bit more about ontologies. This will be very brief because we want to dive into IDO later. Okay, so what is the web ontology language? It is a logic-based language standardized by the web W3C, the World Wide Web Consortium. There are some basic assumptions that we need to take into account, namely every entity that we want to describe in OWL needs to be assigned a type in OWL. And what are these types? So every entity that we come across that we want to put in an ontology needs to be either a class, one of the different property types, or it is an individual. Individuals can be members of classes. Individuals can be related to one another in object properties. Individuals can be assigned a value via a data type property, or we can add metadata via annotation properties. Metadata can also be added to classes. These terms are our primitive objects that we can work with, and we can build more complex expressions using logical connectors and quantifiers, but we don't have variables available in OWL. We can then take these expressions, simple or not, and form axioms. There are two types of axioms, terminological axioms, things that say something like an artifact is a subclass of a physical object, where artifact and physical object are both classes. Or we can have instance assertions, which are of the form a transformer individual is a member of the class artifact, or a resistor and a particular transformer, again, two individuals are connected to one another via an object property. So what is now an ontology? We can make this now precise. Given these axioms, we put a bunch of these axioms together, and when we have a finite set of them, that is an ontology. So the axiom is the knowledge-bearing unit in an ontology. Of course, this syntax is accompanied with a formal semantics, which then enables automated reasoning. It is important that these names, these primitive names that we categorize into classes, properties, and individuals, that they need to be given a meaning outside of the ontology, outside of the logic. And this is something that we as humans assign to them. Otherwise, these are just names and they mean, in principle, nothing to the logic. We assign meaning to them. And then the logic provides us with a formal way to combine these and to make extra statements about these. Okay, so what's now the relationship to knowledge graphs? Everyone talks about knowledge graphs. Well, ontologies, the set of axioms, they can be realized as knowledge graphs, also called RDF graphs. RDF stands for Resource Description Framework, which is also standardized by the W3C. There are different vocabularies made available, also standardized by the W3C, that we can use to create these RDF graphs from ontologies. There are different formats available. We are typically focusing on the turtle format, again, it's standardized by W3C, and it will look something like that here on the bottom right. An RDF graph example you find here on the left. Now, resources in RDF, they are uniquely identified using IRIs, and these are similar to URLs. They can be dereferenceable. So it's very convenient to be able to take an identifier for a resource in an RDF graph and then simply look them up on the internet. There's a web page that tells us all about what this resource is. Note, however, not every RDF graph is an old ontology. Yeah, we can represent ontologies as an RDF graph, but not necessarily the other way around. Okay, so what is this modular ontology architecture that I was talking about? An example you can find on the PCA website. You see this graph here with the orange bubbles. Each bubble is an ontology module. And these blue arrows are the import relationship. If we go to the left here, we see how exactly that looks like. So each of these are the ontologies. And now we see that the ontology identifier is to be declared as an ontology. So this is IDO. On the next level, we have PLM core. This is an ontology published by PCA. The identifier of PLM core is an ontology as well, and it is stated that it imports the IDO ontology. So this here is the IDO ontology identifier, and so on. We can have further ontology modules that import each other in this way, and that simply means in order to use PLM process, you need to import PLM core, and this one needs to import IDO. There are more examples, of course, of these import graphs. Another one you see here in the IO tool that is being developed by DNV, the industrial ontology tool. And here you have an example of a different import graph. Okay, so now let's dive finally into IDO. Now, I need to say something first. The next slide is going to be arguably the most important one and maybe also the most difficult. So I would like you to bear with me and just be patient. It will get easier as we move forward. Okay, so now IDO provides top-level categories. And these are the top-level categories. There are 3. Object, dependent, and temporal. So now what is an object? An object is a class, or a class of objects consists of independent entities that persist through time. Now this sounds like a a head bender. It's like difficult to understand, but you need to read it maybe a couple of times to accept this level of language. It's very general. It's very high level. It is almost philosophical, but that's on purpose because it defines a very general category. The next one is dependent. So the class of dependent entities are inherent qualities or potentials of an object. So on the left, we have objects, and the stuff in the middle, these are things that describe the object. These represent inherent qualities, for example, the weight, the length, the color of something, or they represent what you can do with these objects when you start using them in an activity. Again, it stays on a very, very general level. On the right, these are things that are relating to time or occurring in time. And these are summarized in this class called temporal. Now, we called these classes object, dependent, and temporal. This is simply a choice we made. We could have called them something else. So if the class names sound a bit unwieldy, then you just blame the developers of IDO, but conceptually, this makes a lot of sense. Now, mind you, these are not just arbitrary classes. This is extremely fundamental to make these distinctions, and we will base everything else on top of these three categories. So it takes a while to start accepting this, but the more you read about it, the more you think, and the more examples you see, you will find this becomes very natural and almost beautiful because everything seems to fit. Okay, so now let's maybe one more thing. I talked before about OWL, and whenever we have an entity we want to represent in an OWL ontology, we need to make a decision. We need to assign an entity type to it. We need to say, is it a class, a property, or an individual? When we talk about IDO, even though IDO is an OWL ontology, just the IDO part, the conceptual part, here we need to make a distinction as well. We need to say any entity that we want to represent in terms of IDO, for that entity we need to make a decision. Is it an object, is it dependent, or is it a temporal? So in a very similar way, we need to give it a type. Okay, so let's move on to the next level. There we have a bunch more of categories that subdivide these three upper level categories. On the left, we find the object categories, and there we have physical objects. These are tangible entities that have mass, that occupy a space. So everything you can kick, basically, or touch. Then we have locations. So these are spatial regions. So a room, for example, or that place where we met, or my favorite place to relax. I don't know. Spatial regions, which are different in nature from physical objects. The next category is information object. This includes data and information. The next category is organization, and this includes groups with a common objective. So all these together form the class of object. However, there may be objects that don't fit into these categories. That is possible as well. But these are the main categories under object. Now again, any entity that we want to introduce can only live in one of those. So we can put it in object, but not in dependent or temporal. Once it is an object, we can put it in, for example, organization, but then it cannot be at the same time an information object, a location, or physical object. So it has to be in one. Basically, that's why I draw this, I made these boxes here. You have to respect these boundaries. These are the conceptual boundaries that we have to adhere by. Okay, so the next are the subcategories of dependent, and there we have potential and quality. Potentials are attributes that are realizable through activities. For example, function. So if I run my pump, the pressure will be increased, or the fluid is moving, for example, or things will get hot. Qualities, they are inherent attributes. So my pump will have a certain weight, a certain power consumption. On the right, we have the subcategories of temporal, and there we have activities. Activities are temporal phenomena involving physical objects. Temporal regions are instances or intervals in time. And spatio-temporal regions, these are regions occupied by objects during specific time periods. So I think this is a slide that you should have a look at later again and have a closer revision with yourself and these different categories and think whether this makes sense or not. The more you think about it, that's my experience, the more natural it becomes to accept these and to think in terms of these categories. So these are not arbitrarily chosen categories, something that some people have made up in a pub. This is based on a lot of prior thought and research. Okay, so let's look at examples. Suppose we have a lot of terminology coming from different standards, different reference designation systems, things that we talk about in our application, in our industry sector, domain knowledge. And I don't know how many words there are here, but a lot. And now I would like to use IDO to integrate all of that. I want to use IDO to help with interoperability. I want a common digital language. Okay, so what we do is we take these words, and for each of these words, we need to decide in which of these IDO categories they fall. And we can do that. And here we see the different columns being filled in. So we find that a valve, a mixer, a heater, a pump, or a centrifuge, they are all physical objects. We find that the machining center, the furnace chamber, or the control room, that these are locations. We find that a data sheet or a document or different units of measure, that they are information objects. We find that our companies that we work for or organizations we are involved in, now I use the word organization, that they are organizations. We see that operator, supplier, inspector, vendor, and so on, that they are roles that somebody can take, and that data collection, power generation, transport, that these are functions that something can have, and these are organized under potential. Qualities are things like force, energy, volume, temperature, power, exposure, length, and so on. Activities are processes, something like cooling, heating, injecting, measuring, pumping, separating. Temporal regions are things like machine startup duration, welding cool down period, component time to failure, waiting time for raw materials, and so on. Spatiotemporal regions are things like the route that a forklift takes, a drone trajectory, the construction site area over time, or the product assembly path. So we find that all these words are put now in the right category, and we realize that it couldn't be in any other way. If you move any of these words in a different column, something is wrong. And that is something we have to do. This is work that is not done by IDO. IDO provides the main categories. we have to align with these categories, our terminology. Okay, I think time is running. I'll move a bit faster. These categories are more detailed in IDO, so it doesn't stop at the second level. So here we have the object hierarchy, which goes a little bit deeper. So there's more going on there. If you open the ontology in Protege, you find the definitions of each of these terms, and you see which ones are forced to be disjoint. And when two classes are forced to be disjoint, then we obtain yet another column. Yes, and that means no term can be in two columns at the same time, or in two classes at the same time when they are disjoint. Okay. The same holds for the dependent hierarchy and the temporal hierarchy. I will just jump over these for now for the sake of time. Okay, now you have seen these different categories. Now IDO also provides relationships or relations that allow us to connect these terms between different categories. So we can connect objects with potentials, which are, for example, functions. These names here, these are names for the properties at a high level. There's also a property hierarchy. So there will be a more dedicated name for a function, for a property that connects an object with its function, and that is simply called has function or function of. But the top level category or the top level property is called has potential or potential of. Now, similarly, we can connect objects with qualities or activities, and we can go, for example, from potentials to activities, and so on. There's more going on in terms of properties or relations between the categories. Here, for example, we have relations dedicated to expressing parthood. These are has-part relations. So in each, now notice the pattern, each of these categories are sort of self-contained, or they are closed. You cannot have a part that lives in a different category. So a physical object can only have physical objects as parts. A location can only have locations as parts, and so on. This holds for each of the categories. There are dedicated has-part relations. The top level property is called has-part. For some of these main categories, there are more dedicated names for relations available in IDO. There's a special case for system breakdown. That means we have, okay, the picture changes a little bit. Here you see now we have one big category under object, which is functional object. That is because all the different categories in object, they can be functional objects. They can have a function, and these functional objects can have a dedicated breakdown in order to represent system breakdown structures. I think we will come back to that later in another session to showcase this in more detail. Okay, let's look at a typical modeling pattern for IDO, namely objects, let's say physical objects like a pump, can have functions, and this pump will have, for example, the function of increasing pressure, which is realized in pumping, which is an activity living in a different category. And that pumping has a participant, and that is the pump itself. It will have other participants, namely the stuff that it is pumping, a gas or a liquid or whatever. This is a fundamental modeling pattern in IDO. There's more, of course. So if we want to say that our pump has a certain power, and then you see it gets a little more complicated, that's partially due to me putting these categories in the wrong place. So we have crossing arrows, but bear with me. So we can say that a pump has a physical quantity, which is the pump power. So the power of the pump. We force that the power of the pump is being represented separately from the pump itself. Therefore, we have yet another word for it. So we have pump as a word and pump power. Pump power is categorized as power, which is a subclass of physical quantity, which is a subclass of quality. in IDO. Now this pump power is quantified as, or IDO has this very, so if you read this for the first time, it's a bit unwieldy. You read has physical quantity, pump power, and then quality quantified as, and then you already switch off because it's too complicated. Just understand the logic behind and read these terms 10 times and it becomes easier. I think that's all I can promise. So the pump has a physical quantity, which is its power. It's represented here, and this power is quantified, so a number is being assigned to it by this term here, which is max 5.5 kilowatt. And we categorize this term as a power datum and a maximum datum, and we assign to it a unit of measure, which is this word here, and we point to a number. So this number is outside of this whole categorization scheme because they're treated separately. Okay, let's have a final example, the obligatory pump example. So in our pump world, we have a bunch of vocabulary that we need to deal with. Let's say these are the words that we consider. We put them in the categories in IDO. There they are. The next step would be to, this is the first step is aligning with IDO. So deciding which of the IDO categories these terms belong to. The next one is respecting actually OWL, because we're building an OWL ontology. So we need to assign the correct OWL category to these terms. So let's do that now. I put a little C next to the term to indicate this is a class. Where I don't put a C, this is meant to be an individual. I will ignore properties or relations for now. So now we have aligned with IDO. We have aligned with OWL. Next, we need to relate these terms to one another, at least within their IDO category. So let's do that. We think about it and, sorry, the other way around. We think about it and here are the relations. So the arrows with the empty arrowhead denote the subclass of relationship, and the arrow with the black arrowhead denote the is member of a class relationship. So we find that, for example, artifact is a subclass of physical object. The rotating equipment class is a subclass of artifact. Pump is a subclass of rotating equipment. Centrifugal pump, this class is a subclass of pump. This API 610 OH2 pump is a subclass of centrifugal pump, and this particular pump down here is a member. So this is an individual, and that individual is a member of this API type of pump. Similarly, we treat the terminology in the other categories. Now we may want to relate these terms across the different IDO categories. So let's do that. So we say that our pump has a function which is to increase pressure. That individual is then related to pumping via the realized in relationship. So the pump has a function to increase pressure, which is realized in pumping. And that pumping activity has participants. And here we only have one in this case, but one essential participant is the pump itself to do the pumping. There will be other participants like the medium that is being pumped. Now, this seems to complete the picture, at least for our scenario. Now, what do? We want to end up with our modular ontology architecture. So we put the terms into ontologies. So we find that the top level is already contained in IDO, so we don't touch IDO, we don't change IDO. IDO is standardized, and if you want to change IDO, you need to engage with ISO. So IDO is basically stable, and that's a good thing. In the mid-level or core mid-level, we find terminology that is less general, but also not extremely specific. Sort of, it lives in the right place in the middle. These are words like rotating equipment, pump, centrifugal pump, plant function, pressure regulation, plant process, pumping. This is terminology that can be provided in a core or mid-level ontology. And then further down, and the more specific setting, where we model our particular application or project, there we find vocabulary that relates to our scenario, and that would be this particular pump in my plant, this particular increasing pressure function for my pump that is meant to increase pressure in a particular line in my plant, and so on. So very particular, specific vocabulary is being contained in the lower level ontology. Note these relations, they have a prefix LIS, which stands for Life Cycle Information System. That relates to IDO. So we could replace this with IDO. These are relations coming from IDO. We don't put them in our low level ontology. We don't redefine terminology coming from IDO or imported ontologies. So this is how we can derive a modular architecture for our scenarios. Now, of course, there's a lot more to consider, but this is the basic scenario that you should have in mind. And I hope this gives a good starting point for working with IDO. There's a lot more to consider. You find this vocabulary in IDO and the vocabulary that is provided in reference data libraries that are aligned with IDO. Again, what does it mean to be aligned? It means to respect the different categories by IDO. So you find that reference data libraries that are aligned with IDO, they are maybe difficult to use. It's it's not prescriptive enough. You find there are too many options. You can do it this way or the other way. And in order to overcome that, we have, again, published on PCA websites, we have a number of modeling patterns that have been developed in the Ready Joint Industry project. And I think arguably the most important one or the most interesting one for you to start with is the unit of measure context modeling pattern. I would suggest we look into this next time and go through a particular example. I think for now, we are actually just right on time, out of time, and we need to stop here. I say thank you to you all. Please comment in the chat or send us an email. So what you like, what you didn't like, what questions you have, and we will get back to this next time. As promised, I added slides on the different use cases that are just following this presentation. This is the use case on pump with firmware, pump station, supply chain in chemical industry, asset model transformation, valve ontology, the FMEA failure mode and effects analysis, and the pump life cycle. And finally, we also have a list of references to papers and presentations that you can consider. So you will find that in the slides that we will share with you. And with that, I stop and I hand back the word to Nils.
You are muted, Nils.
Let me share the screen again. Hope you can see the screen now.
We can.
Next Friday, we will have a question and answer and discussion forum. So, and that will be on IDO and DEXP, and really how to use IDO to represent DEXP, and also the other way around. So if you have questions, if you have things you want us to discuss in this next Friday, please send it to us, and we will come back to that next Friday. The recording will be uploaded on YouTube, and also the presentation will be available through the PCA website. I had hoped to have that ready by today, but we need a little bit more time to get it done, so it have a reasonable quality, I would say. And then I thank you so much for showing up. Quite surprised last time that we had this many, and even more surprised this time that we had the same number of participants. So thank you so much.
Thank you all.
Goodbye.
Thank you.
Thank you. Goodbye.
Thank you. Bye-bye.